break. We're going to get started. Have a seat, everybody. I did say at part of the end of the previous talk, I did start introducing Dr. Leon Lee, but I'll do it one more time. He's an assistant professor at the School of Electrical Engineering and Computer Science, joined this year. He did get his PhD, master's, and undergrad degree all from UC San Diego in computer engineering, and his areas are in hardware security and a lot of other things around hardware. So it's a great pleasure to have Dr. Leon Lee join us today. Please join me in welcoming him.
Very much, Mr. for the introduction. It's my great pleasure here to share a general introduction about hardware security. I'll start by explaining these computing stacks. Nowadays, any engineering project is getting more complicated than before. It's very difficult to build everything from scratch. Usually when you're building an application, it depends on some certain platform, right? Whether that's the operating systems or some service providers that host your applications. And these platforms will also run on top of some infrastructures like Amazon Web Services. They provide the necessary computing resources and all the compliance requirements for the applications running on top of it. As we knew, last week or the week before, there's a Canvas incident at the platform level. And when that happens, any applications that run on top of that platform will also be affected. Right? Similarly, if the underlying infrastructure gets compromised, then anything that runs on the Amazon Web Service will also go out of service. And I experienced that last year in October 20th. On that day, I just came here, I was setting up my place, and I bought a Ring security door cameras. And there's an Amazon Web Service outage on that day, so I could never log in. So, I searched online, I contacted customer service, and eventually I realized there's a system-wide outage of these cloud computing providers that is affecting not just the Ring camera, but it also affects United Airlines, Reddit's, PlayStation platforms, and everything, right? This is really the dominant force that provides service for a lot of companies. Similarly, when we look at our electronic devices that we interact every day, we have applications running on top of the operating systems, which run on top of the firmware and eventually on the hardware. You can think of it as a barrel, right? If there's a hole at the bottom of the barrel, all of the liquids or oil will just leak out. And that tells us how important hardware security is. This is the foundation of anything that runs on top of it. No matter how good you design your applications or the operating system, if there's a hardware failure, then your overall system will not be secure. Okay. So this is the outline of today's presentation. I'll start by talking about how someone can exploit the leakage from hardware through side channel attacks to break cryptographic keys. And actually, Fenghao's presentation gave us a very nice foundation. We're going to go over many of the similar topics like encryption, things like security reduction, and also how noises or variations in the hardware language can be used for attack purposes and also defense purposes. Then I'll move on to designing secure systems, starting from a hardware root of trust. By explaining what is hardware security module. This is a very foundational block that exists in every modern chip, going from Intel to AMD, NVIDIA, and Qualcomm, for example. After that, I'm going to take a step back and talk about how to protect hardware itself. Because nowadays, designing and manufacturing a chip involves a lot of companies and entities spread it across the globe. You could get an IP core from the UK, you can get the manufacturing device from Netherlands, do the fabrication or do the design in the US, and maybe send it out to Taiwan for fabrication. So when we share intellectual properties and integrated circuits across this supply chain, there are a lot of opportunities that someone could steal your intellectual property or compromise your design. And finally, I'm going to talk about what are some necessary moves for us to move into an open world where everything can be openly integrated and disseminated, and that is ready to build security in a white box. So starting from the first section, I'll talk about side channel attacks. So side channel attacks exist not just in software or hardware, exist in our everyday life. Think about this keypad that one might put on a door. And usually for a door entrance keypad, there's a static password that nobody ever changes. So after several years of usage, you could see some words on the paint that tells you what are the numbers in this security code. Right? It's going to be 3579, or a different mix of these 4 digits. Similarly, for an ATM keypad, right, you may say, well, different people under different pin codes. So how could someone learn it to side channel? Well, maybe right after you input your pin code on this keypad, I'm going to take a infrared camera to see what are some hotspots on this keypad, right? And the button that you press most recently will be warmer than the other buttons because our body temperature is a little bit higher than the ambient temperature. And if you look at this thermal map, you can see, well, the button 1, 4, 5, and 8, they get pressed for the most recent pin entry. And more importantly, right, the cooler ones, relatively speaking, is probably number 4. The hotter one is probably number 8. So the true password should probably be 4158 with very high probability. Right? This is how side channel information, something that they're not directly compromising the cryptographic operation behind this pin code, but rather they just look at the interface and see what are some leftover traces that can be exploited for security compromise. Similarly, right, when you press the pin code on your cell phone, different buttons will have a different sound, and that sound wave can be learned, extracted by the attacker to infer what is the number that you just dialed. Even for an ATM keypad, right, that produces no sound, but because these buttons are placed on different parts of the metal, they might produce ever so slightly different vibrations, and that can also be captured with a high precision microphone that is placed near the pin pad. And together with some machine learning, one can also infer the pin code that just got entered. When it comes to the hardware space, usually people use side channel attacks to break cryptography, right? They're not going head-on with AES or ISA or any of the hash functions. Rather, they find that eventually any of these functions will run on a hardware platform. And when they get executed, they will emit all kinds of signals that are not directly related to the functionality. Things like electromagnetic radiations, power consumptions, or they might produce different execution time depending on what is the key value that's being entered and what is the current plain text that gets encrypted. And many of these side channel informations can be used to also infer the secret key. I'm going to focus on really 2 categories of side channel attacks. One of them is a direct physical side channel. Someone needs to have physical access to this device to do measurements for electromagnetic radiations or power consumption. They have to tap into the power rail to see what is the current voltage and frequency. The second category is related to the execution time, right? How long does it take for a particular operation to complete on the underlying hardware? And some of these side channel exploitations based on execution time can also be launched remotely. That does not require direct physical access to the device. So starting from power side channel attacks, well, we know in this encryption algorithm, they usually consist of multiple rounds of operations that allow every key bit to be propagated to a lot of the intermediate and final ciphertext. And they also have a bunch of replacement operations so that they achieve both dissemination and the confusion of the underlying data. And when we run this algorithm on a piece of hardware, whether that's a CPU or some dedicated crypto core, you can see pretty clearly how the power trace corresponds to each round of the operation. Right? So this DES algorithm has 16 rounds, so we see 16 cycles of power going up and down quite regularly through the power trace. This is really what we call simple power attacks. We just look at this power trace and see if we can get some information about the secret key. It's actually quite difficult. It's almost impossible to do by bare eyes in this diagram because there's a lot of noises, right? And the impact of the key value is quite subtle among these power traces. To make it actually an effective attack, we have to run what is called differential power analysis. So instead of looking at a single piece of power trace, we collect a huge amount of power traces. Let's say at least 1,000 different power traces. And then we want to analyze multiple of them so that the noises cancel out, and eventually we're left with a clear view about how every key bit affects the underlying operation. The exact way they work is that they want to take a hypothesis. So let's say I assume my key is key number 1. Is it the correct hypothesis? Well, we could try to simulate this key value through this crypto algorithm and get some internal ratings. And then for all of our collected power traces, we're going to sort them according to this internal rating. Essentially sort these observed power traces according to a predicate that is only true if our key hypothesis is correct. And we're going to run into 2 results, right? If our key hypothesis is correct, then this sort is meaningful. Therefore, between the multiple groups, it's going to be a quite significant, differences in their signature. However, if our key hypothesis is incorrect, we're really just doing a random sorting. The way we sort them is completely irrelevant to how things were executed, and therefore, there's going to be no difference between these two groups. On average, everything will cancel out, right? They appear indistinguishable. So this is how we, get rid of all of the noises and crack to the core of the problem to make key recovery, usually by observing the initial run and the final run of the encryption algorithm. Because in the middle, things are significantly scrambled, but at the beginning and at the end, there's a relatively lighter degree of confusion and diffusion, allowing some opportunities for key recovery. And what we just talked about is almost like a direct side channel attack through physical access to the device. We have to measure its power, right? We have to, insert these probes into the surrounding area, the surrounding power rails to measure the voltage and current, for example. But in computer architecture, right, there are also opportunities for indirect side channel attacks, things that can be done without physical access. So this allows a scenario like this when you're probably using your cell phone to do some computation, to run some programs, run some codes at the moment. But me, I could try to get into your device through a remote channel by either running a different application on your device or maybe even running some cloud services, and indirectly learns what you are running and the secret that is being used in your device. And many of the vulnerabilities underlying this indirect side channel attack comes from the performance optimizations that people embed in modern CPUs. We have pipeline, right? A bunch of instructions that have to be executed. Instead of waiting one to complete before initiating the second one, we put them in a pipeline so that they go in this staggered fashion every time we're fetching a new instruction, and another old instruction will just get completed and will be thrown out of the pipeline. And this allows a much higher throughput within the same amount of resource. The other feature that is quite common in modern processors is cache. We know that within a processor, there's some registers, right? They hold some values, a few words. In the memory, you have a much bigger place to store values, but memory is much slower than the internal registers of a CPU. Therefore, if you're trying to access some data from memory, you might have to wait a few hundred cycles. To accelerate that process, people create a cache that sits between the CPU and the memory. A cache is really a small memory that is, has a higher capacity than CPU, but much quicker than the main memory, right? So you buffer some of the most recently used, most commonly used data in the cache, hoping that it's going to be reused in the near future, therefore allowing you to access it much more quickly. The third feature that's really what allows modern CPUs to run even faster is called speculative execution. So let's say you get into a branch, and this branch depends on a value that is stored in the main memory. So the branch is going to take a few hundred cycles to complete. In the meantime, what do? Right. There are really two sides of the branch, right? Branch is taken, branch is not taken. So the condition is true, condition is false, for example. Right. So what we can do is that we can speculatively execute on one side of the branch by taking an educated guess, right? And that can be based on a lot of historical information, right? Historically, which side of the branch is taken more frequently, things like that. So if our prediction is correct, then we really suffer no performance loss because our prediction is correct. So before that prediction is resolved, we already executing the correct side of the branch. If the prediction is wrong, then we can just throw away this speculative execution without letting them impact my internal status of the processor. So the idea is that if prediction is correct, I gain a lot of performance. If prediction is wrong, I lose nothing. So how do these several features come together to produce side channel weaknesses of a CPU? Well, I have this attack called Spectra. This is actually a very famous attack that happened a few years ago. So think of a scenario like this, right? You have an array that is stored in the memory, and someone is trying to access a value that is outside of the array in the secure area, right? Typically, this is a quite standard overflow attack. You can access an array, but the data that you're trying to get is sitting outside of that array. However, if you look at this code, right? This code is actually quite nicely written in the sense that we're checking the index against the array size. So if someone is trying to access an index outside of the array, then this code should not run, should not do everything, right? Condition is false, we should just bypass any of the subsequent executions. However, what could happen is that, well, there's a speculative execution happening at this branch. So instead of waiting for the array sites to be available from memory, the machine, the CPU, is going to take an educated guess, and maybe that guess tells the CPU, you should assume that the branch is taken, right? And try to do that tentatively. What's going to happen in that scenario is that, well, suppose you're trying to access this index that is sitting at index 80 relative to the array 1, the value inside is 0, 9. So what's going to happen is that, well, suppose that machine predicts the branch to be true, then it's going to read at this address, array 1, index x. It's going to try to read this value, and then use that to index into array 2. And this will put array 2 into the cache. However, a little bit later, the machine might realize, well, my branch prediction is incorrect. 80 is out of my bounds. So I should not commit any of the work that were completed during this process. They should be thrown away. And indeed, they're thrown away. I never really store the value from array 2 into the register Y. However, in the meantime, because we have this cache, and cache is like an intermediary state within the machine, the array 2 might have already been brought into the cache, right? It's never used, but it's sitting in the cache because it has been accessed recently. And therefore, if someone wants to learn the value at this address, what they can do is that they can query each and every index in array 2. Array 2, index 1, array 2, index 2, array 2, index 3, etc., etc. For many of these indices, between 0 and 8, for example, they have never been accessed before. Therefore, they are not in the cache. So reading them from array 2 will take a long time. However, index 0, 9, which is just recently fetched from the memory into the cache, was already in the cache. Therefore, accessing index 9 on array 2 will appear faster than accessing any other indices. And this is what allows us to learn the secret value without directly accessing that memory location. We rely on the speculative execution and the cache mechanism within the processors to indirectly load this value, 0, 9, into the cache, and we observe it through some smart manipulations of array 2, things that we can indeed access. So I've talked about two kinds of side channel attacks, right? The power side channel for DES and this side channel for CPU based on the timing behaviors. The reason why power side channel happens is because the encryption process manipulates data-dependent intermediate values, and that causes measurable differences in power consumption, timing, radiation, cache activity, etc., etc. So really, they're not going head-on with AES, DES, or any of the other encryption algorithms. They are going after the implementation of these algorithms, and when they actually run on the device, inevitably, things will not go in a perfectly balanced way, and those leftover traces can be used for key inference. Whereas for CPUs, that's really because we're building all of these performance features into the CPU, speculative, cache, and while they benefit our performance tremendously, they also produce observable physical behaviors. Solving them is actually quite difficult. Not in the technical sense. Technically, you can come up with solutions. You can try to inject some noises. You can try to equalize the power consumption. You can just disable branch prediction, disable cache entirely, and that will eliminate many of the side channel leakages. However, it's also an economic and ecosystem problem. Who's going to take the performance hit, right? As a consumer, do you want to lose 50% in performance for these additional security augmentations? Would the CPU vendors build those performance for 20% extra cost without passing that cost on to the consumer, right? These economic questions makes it extremely difficult to fix side channel or many of the hardware-oriented vulnerabilities. And recently, I ran into some interesting directions about side channel attacks. One of them is about on emerging chip design and manufacturing technologies, there are new channels where things get leaked. So some of you might have heard about chiplet. This is an idea when instead of building chips next to each other or putting them on a piece of PCB, we put integrated circuits, dies on top of each other. So there's a logic die, there's a memory die. You can even stack logic die on top of logic die. It's a way to increase the density by going in the vertical direction. And in that scenario, we might be integrating chips from different vendors, but they still share some communication interface. They might even share the same power delivery network. And that creates additional opportunities for one die to spy into the inner workings of the other die. Another direction, this is really, over the past maybe 5-6 years, people are still working on this, is to develop more sophisticated control and observation mechanisms. Because, given the basic side channel attacks, people have actually built some defenses, but there are always some workarounds. With a very detailed understanding about what are some security features, how people organize them on a chip layout, we can come with more intrusive or more manipulative ways to control the chip. For example, by tweaking the voltage, tweaking the frequency, and that is a more active way to inject fault rather than waiting for it to happen based on the typical process variation. Therefore, we can have a higher resolution. We can let these key values show up more significantly. So as I said, solving them is difficult. It's an economic questions, but people are still putting in some efforts. And the way that these solutions are implemented in the industry nowadays is through hardware security modules. This is usually a dedicated area within the processor that handles a lot of these security sensitive operations. So what do we need? What kind of security do we need in integrated circuits? I would like to argue that there are two different directions. The first one is that we want a separation between normal world and security sensitive world. Right? Ideally, we want them to be executed on completely different hardware devices, but that's probably a little bit not so realistic, right? Instead, at least I want some separation so that maybe they're not, using any shared memory, or maybe I don't allow anything from the normal world to peek into what is happening in the secure world, right? Or maybe when running the secure world, I want to disable the normal world entirely so that there's no opportunities that someone could spy into my secure execution. The other feature that we may want in a modern processor is to have some fundamental security primitive capabilities. As Feng Hao said, every day we're interacting with cryptography, right? Whenever we access a website, HTTPS, we're running some encryption. So in a CPU, we probably want to have a dedicated component that accelerates this cryptographic operation while in the meantime being hardened against side channel and some of the other security vulnerabilities. We also want a way to generate true random numbers. And that is really needed for a lot of normal operations, but more importantly for a lot of security features, such as generating a fresh key, right? Or initiating some key exchange protocols between multiple parties. Sometimes we also want a way to uniquely identify a chip, right? Making sure that, this request originates from device 1, not device 2. And every time when I see the request, I can uniquely identify what is the origin of the request, right? So many of these security features should also be part of the hardware security module. And indeed, most of the semiconductor companies, they're already building these capabilities into their chips. Intel has SGX, something like security enclave. ARM has the trust zone. They also call that a trusted execution environment. And Apple has a security enclave. Security enclave is really, on every iPhone, there's a chip that handles security operations, including store your Apple Pay credentials, storing your Touch ID or Face ID credentials, right? All of that happens on a dedicated area within the SoC. So in general, these security modules handles cryptographic accelerations. They generate true random numbers. They provide a small area for tamper-proof and tamper-evident storage. They also allow isolated secure execution and secure boot and attestations. Every time we power up the device, these chips would already be up and running to provide the initial authentication for the firmware and subsequent boot request. So in terms of hardware designs, right, we still have to build these capabilities as a piece of chip, as a piece of circuit. And many of them are built based on this component called ring oscillating. This is really, a sequence of inverters connected into this chain. It seems to be a very weird construction, right? Typically, for combinational circuits, you don't want to create these kind of cycles. It's just going to run indefinitely, right? Alternating between 0 and 1, 0 and 1, et cetera, et cetera. But it is exactly this oscillating behavior that allows the construction of some security primitives. For example, right, when you build this inverted chain, it's going to have a certain frequency, right? The frequency in which things go from 0 to 1 to 0 to 1. there's a nominal value depending on the delay of every gate, the wire length. But in reality, once we build integrated circuits, we fabricate that with 3 nanometer or 5 nanometer technology, things will not be perfect. Things will divert a little bit from your nominal value. And that's simply because in this, this is a physical process. We are depositing some metals. We're doing a lot of mechanical and chemical processing. It's not going to be, if we want this wire to be 1 nanometer or 5 nanometer long, it's not going to be exact that number. It's going to be 5.00023, right? And that variation creates some deviation between the design specification and the actual physical behavior. So for example, if this ring oscillator has a nominal frequency of 10 nanoseconds, but in reality, it could be somewhere between 9.8 and 10.2 following a Gaussian distribution. Therefore, if we sample it at precisely 10 nanoseconds, we could get either a 0 or 1, depending on whether it runs a little bit faster or a little bit slower. And that is a way to generate a random number through clock jitter. We can also use that to enable unique device identification by building things called physical unclonable functions. So when we put these oscillators on each and every chip, right? We have like thousands or even millions of copies of the dice. Every one of them is going to have a slightly different process variation, and we can monitor that behavior to generate a random value that is unique to each chip. And if we have 100 of these copies, we can generate 100 unique identifier for every chip, allowing for chip tracing or use that as an identity when the chip interacts with the outside world. There's still some open questions, despite the industry-wide adoptions of hardware security modules. One of them is that inevitably there's going to be some interactions between the security module and the outside world. They have to communicate, otherwise you're not even connected to anything, right? You're just doing your own computation without outside environmental support. The other issue is that some of these security primitives are sensitive to the environments. If the attacker actively manipulates the environment, changing the frequency or even physically injecting a fault into the device, it could compromise entirely the source of entropy, therefore compromising the quality of the randomness. Aging is another problem. So once you have used our device for 5 years or 10 years, then the variation is going to go from a Gaussian distribution into a very biased distribution. Right? So that's also another way that randomness could be compromised. And both of them are open questions that people are still investigating nowadays. So I figured it's probably a good time to take a break and take some questions, because I'm going to move on to some quite different topics. Any questions? Yes.
When you mentioned like probing these programs, let's go. When you probe programs, it sounds like, and then like induce entropy, what kind of tools are you using to do that?
Yeah. So when we talk about hardware-oriented probing, usually that requires a direct physical access. We can probe it by physically inserting a needle into the layout, into the peripheral wires coming out of the chip. That is a very classical way of probing. You can also run some non-intrusive probing, like putting the chip under an electron microscope and then optically observe what is happening. You can read the register values by just optically observing what is happening. You can do probing by monitoring the power behavior. Where are the heat spots on integrated circuits? You can do probing by destructively taking away the packages of the chip and then putting a very high precision needle into the internals to even read the values that is transmitted between one gate to another gate.
Okay.
Many of these reverse engineering technologies are quite essential for chip fabrication. They have to make sure that there's no manufacturing defects, and they spent already millions of dollars creating these equipments. They can be used for that benign purpose, but they can also be adopted for malicious purposes.
Okay. Okay, thank you. Also, when you mentioned taking a chip apart, I've heard that with some of the chips that they put like a filament on, so that if you try to take it apart, it actually ruins and destroys the chip. So how would you go about taking apart the chip if there's that type of
there are indeed some
protection?
solutions that makes it much more difficult to destructively reverse engineer a chip, right? We can call that tamper-proof or tamper-evident design. So once the chip gets being reverse engineered, then it will destruct itself. And this destruction could be triggered by either physical processing, when someone is polishing your chips to expose the internals, can also be triggered by fault injection. It can be triggered by some of the other probing technologies. So people did try to harden the integrated circuits against reverse engineering because because some additional resources, right? So it's not really widespread. Oftentimes, for most of the commercial products, we don't have any hardening techniques embedded into these chips.
Thank you.
Perfect. So I'm going to move on to the next part of the talk, which is protecting hardware itself. Integrated circuits are designed in a globalized supply chain, right? We need a lot of cross-border collaborations simply because, for any industry at this scale, horizontal integration is a lot more efficient than vertical integration, where one company handles everything, right? With horizontal integration, different companies develop specialization in different areas at very high efficiency, and that is really the most efficient way to develop integrated circuits in this rapidly changing world. We may have IP vendors, people that provide you with the hardware code in Verilog or VHDL, chip designer who puts everything together, and then foundry and semiconductor assembly and test facilities. They actually do the manufacturing work to convert your blueprint, your layout, into a real physical IC. And finally, it's going to be disseminated all over the globe in a commercial environment, right? So in this process, integrated circuits are moving through the hands of many parties. One of the things that people have identified as security vulnerability is called hardware Trojan. So for example, when me as a designer sends my chip for fabrication in a foreign country, they might have modified my design by embedding a hardware Trojan, right? We must have heard about software Trojan. People compromise their software code, but the same compromise could also happen for a hardware design. The question is, how do we detect it, right? As an IC designer, how do I make sure that the chip I received out of manufacturing is the same as the design blueprint I sent out earlier? Well, if you can look at these two pictures, it's pretty easy. But in reality, the designer cannot really see the internals of the chip very easily. The reason is because out of manufacturing, we have thousands or millions of copies of the chips. And if you want to see the internals, you have to reverse engineer each one of them. And that is a very expensive process. More importantly, the Trojan might have been, in fact, inserted into only some of these chips. So even if you spend some efforts to reverse engineer a few of them, that might not allow you to actually find the Trojan-infected chips. The question is, between this blueprint that we designed earlier and all of these fabricated ICs I received out of manufacturing, how can I make sure that they're really the same? And this is really another creative use of side channel analysis. We analyze their similarity in terms of power traces or electromagnetic radiation traces. So what this diagram shows is that, well, starting from the layout, this is my original blueprint I'm sending out for fabrication. So after all of these chips are fabricated, I'm going to apply some test patterns and collect a lot of power traces. I'm going to compare these collected power traces on my fabricated products with the original simulated power traces on the original blueprint. And if they match, that means they are the same. If they don't match, that means something has gone wrong in the manufacturing cycle, right? That's only the ideal picture. In reality, well, there's always some precision issues about the simulation. There's process variations that could impact the accuracy. So people would also go through some calibration process to make sure that our simulated model is an accurate representation of the real manufacturing environment, and eventually use some machine learning to classify good chips and Trojan chips. One of the important parts in this process is to actually identify the stimuli or test patterns that we use to generate power traces. If these patterns are high quality, they can trigger a lot of the Trojan activities, therefore magnifying the power differences. So one of the things we investigated is what kind of stimuli and patterns do we use for simulation and testing? And we find that we should really try to activate a lot of, a big region of the IC so that there's a higher likelihood that the Trojan logic can be activated. But on top of that, we also want to refine the test patterns further using a technique called superpositioning. It's also similar to differential power analysis when we take multiple power traces and let the background noises cancel out. And with that, we're able to squeeze the region within which we're observing the Trojan and eventually letting the Trojan fall out of the nominal distribution of noises. Hardware Trojan is one threat where people modify your design. Reverse engineering and piracy is a different threat where people take advantage of your intellectual properties, right? So again, you send this chip for fabrication in a foundry. You ask them to fabricate 1,000 copies. What prevents them from making 2,000 and sell the other 1,000 in the open market or in the green market? And that has happened since the very early days of integrated circuits. This is Intel 8086, right? The very famous 8-bit x86 processor. And then it has been direct photographically cloned by some Soviet companies. They really look identical because the company took the Intel chip, reverse engineered it, get the exact layout, and then just replicate that one by one into their own chip. They appear identical. They have the almost identical capabilities. But reverse engineering could also be more complicated, where someone, they don't just look at your design, but they understand what is happening. They try to understand your design philosophy, right? What are some features that you build into it? How you handle branches, how you handle pipeline, how you handle caches for modern processors. And they can use that knowledge to design their own version that is even superior than the original version. And that happened by NEC, which is a Japanese chip manufacturer at the point. They reverse engineered the Intel processors, created a pin-compatible but higher performance version of that processor. If this happens in modern world, it's going to cause a lot of damages to any chip designers, right? Your competitor is going to create a better version of your design, even though you initially spent millions of dollars in the research and development. The solution to this problem is called logic locking. Instead of sharing the original design to fabrication, we let it go through a process called locking, where we modify it with some additional key control signals, right? This is like an encryption for integrated circuits, but we don't share the key value with the foundry. We just send this locked version for fabrication, and afterwards, once the chip gets back to my hands, I'm going to load the key values into the memory to reactivate it, right? To let it come back to the original functionality. And hopefully, because the key is never shared with external parties, they couldn't use your chips. They couldn't understand what is happening. They couldn't reverse engineer it. So your intellectual property is really safeguarded. I want to show you because it's almost reaching 2/3 of the presentation and people are getting a little bit tired, if not hungry. So I'm going to present this pasta recipe analogy about logic locking, about locking or encryption in general. Suppose there's a pasta that you want to encrypt, or pasta recipe maybe, right? This is this is not a standard pasta. It's not Alfredo or marinara. This is probably like garlic puree together with basil leaves and some Parmesan cheese, right? Like a creative recipe, let's call it. Logic locking or encryption in general is trying to break down into smaller pieces, control everything by a key. It is only when we put the correct key that we can recover the original recipe. Otherwise, it's going to land on some other, I don't want to call them garbages, but non-traditional pasta dishes. So in terms of how we can recover the secret key, there are a few channels. There could be a functional weakness, right? If someone has actually tasted what the correct dish is supposed to taste like, they can search in the key space to find out which one gives me that identical taste. And in the hardware domain or in the cryptographic terms, that's called oracle-guided attacks. We know what we should expect, and we try to find a key that delivers that expected functional behavior. The second category of attacks on logic locking is called implementation weakness. The way people break down that original recipe into these smaller pieces might be done through a deterministic and predictable process. And if we can learn that process, we can just reverse it, right? And then recover the original recipe. And what we found is that there are also some structural weaknesses. Like even if we know nothing about what the dish is supposed to look like, we can look at all of these activation possibilities to figure out which one is correct without any additional knowledge, with no side channel information, with no structural information, with no implementation information. So purely looking at these activation possibilities and see which one is reasonable. So I'll start by going through quite briefly about the functional weakness. So this is a logic lock circuit with one secret key. And with functional attacks, we assume that the attacker also has access to an oracle. This is an activated circuit that produces the correct behavior, but we cannot see the internals. This is like a black box. Right. What we can do is we can send some input queries to the oracle. Right. For example, putting input AB equals 0, 0, learn what the correct C output should be at 0. And then we come back to this log circuit and ask ourselves this question: which key value would produce a 0 on the C output, given that A and B are both zeros. With a single bit key, it's pretty simple. You use one pattern. Usually, when you have dozens or even hundreds of key values, you have to find a smarter way to navigate in that key space to apply smarter patterns, right? But little by little, you can eliminate all of these wrong keys, leading to key recovery. Implementation weakness is exploiting the fact that the synthesis and logic locking algorithms are not perfectly random. They go through a particular process, right? They insert a key gate and they do some manipulations, move gates left and right, so that we're trying to confuse the mapping between the key gate type and the original functionality a little bit. But that process is not really solid science. It's more like some obfuscation, some quite primitive obfuscation techniques. So once the attacker has learned how this locking and synthesis process works, they can just predict what has been done to this lock circuit and reverse it entirely. But we find that even without any additional functional or implementation knowledge, we can still break logic locking. And the idea is like this, right? There's a pasta recipe for different activation possibilities. We just try to enumerate them. But now how do we tell which one is correct? Well, I know that this is an integrated circuit. This should have satisfied some performance optimizations, should have a smallest area, should have low power and everything like that. We know that it should be a rational integrated circuit, or in this analogy, it should be a rational Italian dish. Right? Putting ketchup on pasta is definitely not an Italian dish. Putting pineapple on pasta is really a big no-no. Italians will never snap spaghetti in half. And therefore, by just reasoning about which one is rational, we're able to find out, wow, this dish looks delicious, looks authentic. So this must be what that recipe is trying to convey. Right. Coming back to the logic locking example, again, look at this circuit. I can try to put two different key values, key equals 0, key equals 1, and see which of the circuit is more rational, is more reasonable. We find that, well, one of them is quite reasonable. Every gate is doing some functionalities. No one is idling, right? They're contributing. Every gate is contributing something to my computation. Whereas in the other circuit, some of these signals are really stuck at 1, which means you can replace that signal with a constant 1 without changing the output functionality. That means a lot of these circuit components are really meaningless. You can just remove them and replace that with a constant 1, your power rail, right? So this should never be a reasonable circuit that someone has obtained out of the design process. Therefore, this is incorrect. This is incorrect. We made this key inference without any functional or implementation knowledge about the locking algorithm. Given these three categories of attacks, it has become quite difficult to develop a good logic locking solutions. The idea is that we want to provide a strong protection or corruption to the original circuit functionality and structure to prevent someone from learning it. But as we're embedding those significant structural and functional modifications, we're also inevitably increasing the key exposure. Because every time when something goes wrong, either functionality-wise or structural-wise, that's telling me that certain key values are incorrect, and that provides a lot of key pruning choices that eventually leads to key recovery. To solve that problem, we also came back to the original standpoint. Think about at high level, what are some levers that we can use to control security solutions? The secret key is definitely one of them, right? This is something that we artificially embed as a secret that only the designer knows. But in the meantime, there's some other sources that can be used to extract hardness to give us some additional levers for building secrecy. One of them is that the original design is another thing that only the designer can access. Once it has been logged, no one can see the original design. So if we can extract some internal secrets from the original design and use that to also control the locking and obfuscation behavior, then we're really buying ourselves some additional advantages. The way it gets implemented in this example would be, well, instead of using the external secret key to protect every piece of the functionality, what we do is that we analyze the global interaction of all of the functionality pieces and try to find a way to minimize external key exposure. We do that by partitioning our designs into a few sections and then use the external key value to control these critical points while letting the internal behaviors control the rest of the obfuscation and locking behaviors. And this minimizes the key exposure to only these a few critical points. between partitions while still maintaining a broad obfuscation coverage. Every piece of functionality is still protected by some security mechanism. And finally, of course, to actually implement it, we have to come up with a way to assign the partitions, to convert that from a diagram blueprint into a integrated circuit implementations while supporting the hybrid activation controls through both internal and external secrecy. So the last bit I want to talk about is how to build security in a white box. So far, most of the things we're talking about operate in either a black box or gray box attack model, where the attacker has only limited visibilities to the internals. The side channel attacks on AES, right? It's not really trying to probe into the circuit, it's observing around the circuits. The side channel attacks on CPU through cache and speculative execution, they're also not getting into the circuit, they are observing around it. Attacks on logic locking, well, you have Oracle, but as I mentioned earlier, this is a black box Oracle. You can only use it, but not see the internals. In reality, actually, many of the attack models are closer to a white box. Again, considering someone from the supply chain with very advanced capabilities for fabrication, diagnosis, failure isolation, they have access to this high precision microscope. They have the incentive to learn your circuit by putting in some additional efforts. So we think that in many situations, the capabilities of the attackers are closer to white box rather than black box. Right? And there are just all kinds of different things that people can do in different threat models. The idea is that the more visibilities that the attacker can have, it is more dangerous for the IP right owner. Right? With white box, they can pirate it, they can duplicate it immediately without spending any additional efforts. With white box, you don't have a way to store a secret key value because everything will be exposed. So in general, also at a quite conceptual level, people could get a higher level of understanding either when we intentionally share more of our design, we outsource it more extensively in the supply chain, or when the attacker puts in additional efforts to reverse engineer it. Eventually, they'll get to a level of access closer to white box. So this is a question that we investigated. Our research is how to build some security in the white box model. Is it even possible? As it turns out, there are some opportunities. We cannot safeguard against every problem, but there are certain problems that involve the reasoning process, which can still be hardened in the white box attack model. So consider this scenario when we have a vehicle controller with a lot of different states and different conditions that allow us to move among different states, right? There's acceleration, there's some collision avoidance, et cetera, right? Your inputs and also sensing from the environment provides these signals that allow you to transit from one state to another. And suppose someone, your competitor, another vehicle manufacturer wants to reverse engineer your products. They might be interested in how you implemented a certain acceleration logic. And this is a type of functional reverse engineering. They're not trying to replicate your whole design, but rather they want to get into it and see what are some functionalities that the circuit implements. The question is, how can I make this job a little bit more difficult for the attacker? This, in this, again, graph representation, that means we have a sequence of actions, a sequence of transitions, and there's a security sensitive one that the attacker is trying to get into and learn its true functionality. And the solution that we come up with is to lock everything with a unique key value. That's really an ideal solution. Why do we use one key value when we can use a lot of different key values? In fact, a unique one for each and every state. Well, while this is an efficient security solution, another question arises, how do we generate these many key values while making sure that they're secure in the white box model? We cannot store them. We actually don't have the resource to store them. It's a lot of binary data we have to store. We also cannot store them in the white box model because anything can be directly probed. So instead, we propose a mechanism to generate the key values on the fly. Instead of storing them, rather these key values are assigned according to the internal execution sequence. So as the chip is going through the sequence, naturally it's going to collect all of the execution choices to compile a signature. And the signature is updated dynamically as we're moving through different parts of the design, eventually giving us the correct key value that allows for activation. You may ask, right, in this process, looks pretty nice, but where are we getting security from? Well, we are getting security because the designer and the attacker are looking at different things. The designer can look at this original picture. They can run some graph analysis to learn patterns and to assign keys in a smart way. Whereas from the attacker's perspective, they are not looking at this graph, rather than looking at this gate level or layout level netlist, a bunch of gates and wires and their interconnects. And at that level, to learn patterns that originates from the functionality, it takes a lot of efforts to unroll the circuit to convert this lower level representation into a higher level construct. And that difficulty is what deters reverse engineer from this integrated circuit fabrication process. At a lower level, if you want to go up, it's a lot more difficult than starting from a higher level and running analysis. So the principle behind white box obfuscation or white box defense in general is to not rely on some custom or externally introduced secret key values, but rather build security on top of some more solid foundations that we know is difficult. And this is exactly the concept of security reduction that Feng Hao presented earlier. We can find a hard problem A, and we build our security solution or security protocol B on top of this hard problem A. And if we can show that, well, if someone breaks protocol B, implies they can break problem A, that means if someone cannot break problem A, they cannot break the protocol B, right? P implies Q is the same as not Q implies not P. In the hardware design space, we exploited this hardness of making sequential analysis from a lower level circuit implementation, but there are a lot more hard problems that are open for people to take advantage of. Reliability is very difficult, right? It's difficult to predict, it's difficult to enforce. There are a lot of optimization problems that people don't know whether we're reaching the best solutions. All of these could serve as a trapdoor that we take this problem, we solve it in a particular fashion, and if we ask the attacker to solve it, it might also almost be impossible for them to replicate our original process. Therefore, they cannot easily recover the secret key that we extracted from our original solution to the problem. We have talked about a lot of different angles of hardware security, right? Ranging from how people can compromise the hardware, how the hardware can provide some security feature to the systems, and for the hardware itself, how we can ensure its confidentiality and privacy and things like that. In the modern world, any computation is done on multiple abstraction levels, right? Whenever you send a query to ChatGPT, it goes through the cloud server, the cloud model, and then you have to have some local computation capabilities to do the encoding, decoding for security purposes, et cetera, et cetera. It's going through a lot of different levels. And in order to build an effective security solution in this system, we have to think about not only just the security of one model, the security of one application. We have to think about how to enforce a multi-tier or multi-layered security from the hardware all the way to application. And these different security layers will provide hardening against different categories of attacks. Lower level hardware will provide hardware-oriented defenses in terms of physical isolation, in terms of side channel resilience, right? The application level and the firmware level, they will have their own authentication, their own security policy, handling security coming out of internet interaction, for example. But after all, real-world security never emerges from one perfect defenses. We almost always need multiple layers of defenses because they complement each other, eventually realizing this defense in depth paradigm. And this is the last slide, which I want to also talk about a little bit of extension out of hardware security. In some of these research projects, we find that the solutions that we originally intended for security can also be used for reliability purposes. In this example, we're trying to combine hardware security with error detection. The idea is that logical logging is already providing a way for us to build corruption, right, to confuse the attacker. But the very same corruption mechanism can also be used to enhance the error detection probability. Instead of enforcing direct detection, we let the error propagate within the corruption space almost for free, and eventually achieving a latent error detection at much higher probability and also maintaining a lower cost. Oh, I do have one more slide. Why hardware security matters today. Right. hardware design is efficient. In fact, any algorithm can be implemented in either a hardware format or a software format. There's no algorithm that you cannot put onto a piece of hardware. And hardware usually offers dozens of times of performance benefits compared to a software implementation. And for that reason, many of the big software companies, they're also migrating towards designing their own custom hardwares to accelerate their own computation, right? Google is designing their TPU, Meta is building their own chips, for example. Another source of demand for integrated circuits is because we're moving to this Internet of Things, right? Every device that we interact with has a lot of electronic components, right? In a vehicle, the number of chips grew from maybe 5 or 10 from 20, 30 years ago to nowadays hundreds of integrated circuits. And all of this is underpinning the importance of hardware security because the hardware level needs to be the foundation that provides the root of trust for anything that runs on top of it. So with that said, that concludes my presentation. Thank you very much, and I'm happy to take a few questions despite we are running right on time.
And there is a course called Hardware Security.
Yeah, CPTS for
reverse engineering, and this was a really nice teaser for that course. When are you going to be teaching it?
I hope in the coming school year, in the spring semester.
Take that class, look forward to that. So we are running a little bit short on time, but you did an excellent job. I really enjoyed it, and I will take one question.
I had one. Mine's more of a industry question, kind of, but essentially, for reverse engineering chips, let's say that you were vehicle manufacturer A, I'm vehicle manufacturer B, I'm the bad actor here.
Yes.
Is there like a physical barrier too, rather than just on the hardware and software side? For example, if you as vehicle manufacturer A have access to like TSMC facilities in Arizona or Taiwan, and I have only access to Intel facilities, if I somehow successfully reverse engineer your chip that you designed yourself, is there a physical barrier there too? Just because of the fact that I have access to less prestigious foundries?
That's a good question.
Yeah.
So I had an example about the Intel 8086, right? In 1980s, at that point, the physical barrier is very low. You see the layout, you can almost exactly replicate it.
Yeah, indeed.
Different countries, different companies are having very similar technologies. But nowadays, that's a very valid question. The layout designed for TSMC might just not work at all for Intel, right? There are different process nodes. There's some different process parameters that you have to navigate around. And this difficulty applies to direct cloning of a device. The attacker can still try to reverse engineer it even further to see, for example, in this processor, how do they build their pipeline? What are some additional accelerators that they're putting on top of it to accelerate neural network applications? And once they learn that conceptual or functional understanding, they can build their own versions of chips with similar functionality, following similar principles, but not exactly the same. And that could be better suited for this competitor's own manufacturing capability.
I see. Thank you.
All right, we'll wrap it up there. Thank you again.
Thank you.